Yeah, very welcome to my presentation on the topic compressor design versus refrigerant properties. What affects the compressor efficiency more? And I would like to motivate my talk with a highly topical issue of refrigerant selection. So refrigerant selection usually starts with a list or a database of possible refrigerants and a case study. And then a process model is set up specifically to the case study, and the performance of the various refrigerants from the list is evaluated through the process model. So other approaches add, for example, a molecular design to the process model, and then optimize both the process and the molecule together. So both approaches finally provide a ranking of the best suited refrigerants. And for the process model, it is particularly important how the compressor is modeled. We all know that compressor efficiency has the major impact on the COP. However, the compressor efficiency is mostly assumed to be constant for all conditions and for all refrigerants, just one value. And the argument usually is that similar efficiencies for all refrigerants can be achieved when the compressor is specifically designed to the selected refrigerant afterwards. And yeah, this is a quote from a paper, but I don't want to put the authors in bad light. This could also have been written in one of my early papers. The point is, the assumption has never been proven. Yeah, but if this assumption is false, the process model and also the results might be false. And if we look at data from the literature, we get some doubts about the correctness of this assumption. What we see here for a single compressor are the isentropic efficiencies, and we see that the isentropic efficiencies are strongly refrigerant dependent. But much more important is if we compare data from other compressors from different manufacturers and of different size, we can observe the same trends. Yeah, and that was the starting point of our study. We aim to analyze if tailoring the compressor to each refrigerant actually can overcome the differences in compressor efficiency due to refrigerant properties. And for this purpose, we first derive a loss-based semi-empirical compressor model, and afterward we use a model to simulate tailoring. And from practice, we concluded that two tailoring options seem to be realistic. The first is changing the geometry of the compressor or the displacement, and the second is to reduce individual losses. For example, if a certain refrigerant particularly suffers from friction losses, we could try to reduce friction losses. So we do it based on a model, and the model shall predict refrigerant-dependent isentropic efficiencies for reciprocating piston compressors and for a constant operation of a heat pump. And that means we keep evaporation and condensation temperatures and the superheating and the compressor speed constant. The model shall account only for the major losses, which shall be described by physical equations and fitting parameters. And the model shall be applicable to different compressors with different geometry without the need of refitting the parameters. Yeah, most important, it shall require low computational effort. So we do not aim for highly accurate prediction of the efficiency at a certain operation point and with a certain fluid. This model only shall predict the differences in compressor efficiency due to refrigerant properties. And low computational effort is a requirement that this model will be used in practice. So one definition of the isentropic efficiency that we also want to use is that we divide the isentropic power by the electric power, and the electric power can be written as a sum of, again, the isentropic power and a loss power. And finally, we can write the isentropic efficiency as a function of the theoretical mass flow rate, the volumetric efficiency, the isentropic work, and the loss power. So calculating the ideal mass flow rate and the volumetric efficiency isn't a problem. We have to take care on how to calculate the volumetric efficiency and the loss power. And for that, we derived models for both parameters, which are based on, or which consider the major losses of compressors. And for the isentropic efficiency, we consider friction, flow, and electric losses. And the equation for the volumetric efficiency mainly covers re-expansion after the compression step and overcompression. So in summary, the model has 5 model parameters that can be fitted to data for one or of one specific compressor. To be able to apply the model also to compressors of different geometry, we additionally derived equations that describe how the fitting parameters change with geometry. And we figured out that mainly the friction and the flow loss parameters are geometry dependent, while the dependency can be described by this equation. Okay, now we can fit the parameters, and for that we took data from the manufacturer EPSE of a very small semi-hermetic piston compressor, and then we fitted our parameters, and what you see here are the isentropic and volumetric efficiencies taken from EPSE, and now in red our results, our model results, and we see a very good match. So the model is able to predict the isentropic efficiencies or the differences for different fluids for a constant geometry. So if you now think predicting the fitting data isn't a challenge, we totally agree, and that is why we applied the model to different data sets without refitting the parameters. So we used the parameters gotten from this fitting procedure. And we took 3 additional data sets. 2 are taken from the literature, this one and this one, and 1 was measured by our own. And the special feature is that these compressors are from different manufacturers and of different size. For example, this compressor has a 6 times larger displacement than this one. And furthermore, here refrigerants are included that were not part of the fitting data, here shown in the color orange. So what we see is this, and also for these data sets, we see a good model agreement. And we see a bit larger deviations for this data sets, but in the end, we weren't able to figure out whether the data or the model are responsible for it. However, also for this data set, the trends are correctly predicted. And finally, we see that our model can also be used for extrapolation concerning geometry and refrigerants. So let's come to the tailoring, and we start with geometry. Our case study is a heat pump for residential heating that shall achieve a heating power of 3 kilowatts for all refrigerants. And due to the differences in density, for each refrigerant, a different displacement is required to fulfill the 3 kilowatts heating power. And the required displacements are drawn here. And for example, you see R32 needs the smallest, and R1234ZE the largest displacement. The black dots show the calculated isentropic efficiencies, and we see again that compressor efficiencies are strongly refrigerant dependent, although if the geometry is tailored. And for example, R32 has a 28% larger efficiency than the worst fluid 1234ZE. And if we now compare the efficiencies with the required displacements, we see that fluids with larger displacements lead to smaller efficiencies. So why is that? To analyze that, we must remember the definition of the isentropic efficiency used in our model, and it depends on the isentropic power, of course, and the loss power. So the isentropic power drawn here is nearly constant for all refrigerants, but the friction power and also the flow loss power strongly differ, what you can see here by the blue and red values. And what you see is refrigerants that require a larger displacement have larger friction losses. Yeah? I think that is clear, yeah, because the friction surface is larger. But these refrigerants also have larger flow losses. Of course, the valve area can be increased if the piston diameter is increased, but the volume flow rate through the valves increase even more. And that is why refrigerant with larger displacements, or which require larger displacements with smaller densities, have smaller isentropic efficiencies. Okay, now we tailor the compressor by loss reduction. And what we do is we decrease each loss one after the other by 50%. And that is an extreme case because it would be very ambitious to achieve in practice. And if we do this for the friction losses, we get this line, and we see all efficiencies are nearly equally increased and the differences still exist. And that is not really surprising since the friction losses are very similar for all refrigerants, and every refrigerant benefits from a reduction of friction losses. We get a similar result if the electric losses are decreased. We see again nearly a parallel shift of the line. If we decrease the flow losses by 50%, we see that some refrigerants benefit more than other. And these refrigerants here have larger flow losses, and therefore they benefit more when the flow losses are decreased. However, even though the differences from the best to the worst refrigerants are decreased, the isentropic efficiencies are still different, and the fundamental ranking remains. So our initial question was if tailoring the compressor to each refrigerant can overcome the differences due to refrigerant properties. And our study shows that first, isentropic efficiencies are highly refrigerant dependent, and if we tailor the geometry to the respective refrigerant, we still see differences between the refrigerants and between the isentropic efficiencies. And also, if we halve all losses or single losses, we see, okay, efficiencies slightly converge. For example, if we halve the flow losses, but still there are still significant differences between the refrigerants, and the ranking remains. So we conclude equal isentropic compressor efficiencies for all refrigerants or changes in the fundamental ranking seem unrealistic for reciprocating piston compressors. And a second conclusion is the compressor efficiency should be considered for or in refrigerant selection. And now there is a simple algebraic model that can be used, at least for a first estimation, with very low computational effort. Thank you for listening to my presentation.